Now we are going to discuss about estimation of discharge from an unconfined aquifer. So before going to derive an equation, we should know some terms generally used in the groundwater hydrology. Tupit and Thiem has given some terminology that are used in the groundwater hydrology and also for the determination of discharge equation in case of unconfined aquifer or whereas in case of confined aquifer. So first of all, they have given some assumptions. Now we are going to discuss about first assumptions that are the aquifer is homogeneous, isotropic and uniform thickness. The aquifer has an infinity lateral extent and the well is fully penetrates into the aquifer and receives water from the entire thickness of the aquifer. And another assumption is the flow lines are radial and the flow is horizontal and uniformly distributed for the entire length of the thickness of the aquifer. And last assumption is that the pumping has been continued for a sufficiently long time at a constant rate to attain the equilibrium stage. So what is equilibrium stage? That I will give you later. And another assumption is the flow is laminar and satisfies the Laplace equation. These are the assumptions used Dupit and Thiem. And another one, right. So if we are going to extract water from the well, so we should use one pump because the extraction of water from the ground level to top level. So here where the pumping is not started, the water level in the well is horizontal. So whereas in case of unconfined aquifer, the water level represents the water table existed in the particular aquifer. Whereas in case of confined aquifer, the water table refers the piezometric surface of the particular level. And as the pumping is started, the water level in the well gradually reduces, and this reduces and form a just like a radial flow in and around the well. So it is assumed that this is like inverted cone around the well where we are going to pumping is continued. This cone is known as this depression. We have one radial shape there, that inverted cone. This cone is known as cone of depression. The area influenced this cone of depression is called as area of influence, and this area is known as and the radius is known as radius of influence. Here, and one more point, the water drops from the original level to some level. This drop is known as drawdown. That is in case of unconfined aquifer or in case of confined aquifer. And one more point, when the rate of pumping is kept constant, initially the drawdown curve gradually changes with time. This phase is known as unsteady state because the water table is the function of time. However, if the pumping is continued for some time, it can reaches the equilibrium stage when the cone of depression is stabilized. Where that is gets equilibrium stage, that means the cone of depression, already I told you, this cone of depression is stabilized, then that condition is known as equilibrium stage. At the equilibrium stage, the quantity of water entering into the well from the sides of the well, that is equal to the water extracted from the well by the pumping. So here, once you see the diagram, first of all we are going to discuss about unconfined aquifer and discharge equation from the well. Right here, now by using all these heads, now we are going to determine the equation that is for rate of flow from the unconfined aquifer. This is the unconfined aquifer. The bottom layer is impervious layer. This is the ground layer, a ground surface. This is the water table. So here one side is completely impervious, another side is the water table. This is known as unconfined aquifer. So here in this unconfined aquifer and the water table that is from the water table to the bottom of the well is the thickness is h. This is the well. The water pumped from this well, this is the constant rate, that is at q. So because of the initially this is the water table, initially this is the horizontal level, then this water table fall down from this level to this level. This is known as drawdown. In case of main well, this is denoted by drawdown in the main well denoted by SW, and the water level available in the main well is HW. Initially the water level is capital H, now the water level in the main well is HW. And also for the derivation of equation for the determination of rate of flow, here we are also taking two observational wells. This is one observational well, this is the another observational well that are taken very nearer to the main well. So in this observational well, because of the pumping is continued in the main well, the water level drops from this point to this point. Here, because this observational well is within 300 meters from the main well, so that because of the pumping here also have some drawdown. This is the initial level. This initial level fall down up to this one. This is the drawdown. This is the observation well number 1. The drawdown is S1. And also this is the observation well number 2. Because of the pumping here, there is no pumping in the observation well number 1 and observation number 2. Even though the water level drops here S1, in case of observation well number 2, here the water level drops from this level to this level. This is S2. Right? Here, and also this is the water level in the main well HW, water available up to the HW. In case of observation well, water available up to the H1. This is the water depth available in the observation well number 2 is H2. And also this is the, because of the water level drop here, this is a flow line, radial flow line. Already I told you this is the radial flow line. This is also known as cone of depression. This is also known as cone of depression. And here we have taken one point, that is P. This is the point P. At point P is R distance from the main well and H water level from the bottom to the point P. So this is the diagram. This diagram is useful for the derivation of discharge from the unconfined aquifer. Flow occurs through a vertical sides of the cylinder surface passing through the point P. The area of flow A is equal to 2 pi RH. Area flow from the sides of the well is equal to 2 pi RH. Now we know Darcy's law. Darcy's law is nothing but, Darcy's law says that the velocity of flow is directly proportional to the hydraulic gradient line. So here we have taken velocity is equal to K into I. I is the hydraulic gradient line. K is the coefficient of permeability, I is the hydraulic gradient line. Here V is equal to K into I is nothing but dH by dr. So now we are going to estimate the discharge. Discharge is equal to velocity into cross-sectional area. Here already we know the velocity based on the Darcy's equation. Velocity is equal to V is equal to Ki. A is the, already I told you, that is equal to 2 pi RH. That means the water enters the well through the sides of the well. Then that is based on that phenomena. Here the cross-sectional area is equal to 2 pi RH. Right? Therefore Q is equal to A into A is nothing but 2 pi RH into velocity is this value K into dH by dr. So here in this equation, in such a way that all H related, head related terms are one side and constants and radius related heads are another side. Once we know that here dH into dH equal to Q by 2 pi K into dr by dH, then now we are going to take the limits based on the given diagram. So now we are going to determine the values here. This is the P. P is R distance from the main well, and H is the water level in the at point P. So here we are going to take limits in such a way that R equal to R1, that is the distance between the main well and the observational well number 1. If R equal to R1, this H is equal to H1, that is H of P equal to, that is the water level in the observation well number 1. If another condition is R equal to R2, that is the radial distance from the main well to the observation well, in this case this H is equal to H2. These are the limits. Then these are the limits. These limits are now we are going to integrating this equation both sides by these limits. So then finally we have the equation, that is Q is equal to rate of flow into the well through an unconfined aquifer. Q is equal to pi k h2 square minus h1 square divided by log e r2 by r1. This is the standard formula. Here once you observed here, pi is constant, k is also constant, that is coefficient of the permeability, that is depends upon the soil characteristics, and h2 square, h2 is the extreme well water level, h1 is the inner well water level, and r is the radius of the outer well, that means well number 2, and r1 is the radius of the well number 1. Right here, this is the formula for the determination of flow rate into an unconfined aquifer. One formula for the determination of radius of influence. That formula is R equal to 300, R equal to 3000 SW root K. Here R is equal to radius of influence, SW is equal to drawdown, K is the coefficient of permeability. If they have given radius of influence in your problem, then you are going to take that value. Otherwise, if they have not given radius of influence, then you are going to determine the R value by using this formula. So, and also the radius of influence should be have some limits, that is 150 meters to 500 meters. The radius of influence should be 150 to 500 meters. Average value is taken as 300 meters. This indicates that the wells should be digged in such a way that the well to well distance should be maintained at least 300 meters. So here we have derived the equation for the determination of flow rate into the well to an unconfined aquifer. That is the equation also Q is equal to pi k h2 square minus h1 square divided by log e r2 by r1. Here what we have done, two observation wells are taken apart from the main well, because we are going to spend some more money for the extraction of two observation wells. If there is no, this extraction of this observation wells takes money, that is uneconomical. So that if there is no observation wells, how we are going to determine the flow rate into unconfined aquifer? Here, for that purpose, for the taking of two observation wells, here we are going to take the main well radius, main well water level, and also we are going to take the extreme conditions. That means the radius of influence is touches the ground, that is capital R, that means cone of depression radius, and where that touches the ground, the water level from that level to impervious layer is nothing but H. Now we are going to, earlier we have taken two observation wells, so instead of two observation wells, so now we are going to take one is the main well and another one is the extreme conditions. Here also, as like as earlier case, earlier what we have taken, if P is the point P located on the radial curve, here also P is the point P located on the radial curve. Earlier case, that R is taken as R1, R is taken as R2, H is taken as H1 and H is taken as H2. Just now I tell you. Here, in this case, R is taken as RW. What is RW? This is the radius of the well, this is the diameter of the well. We are going to take the RW. If R is equal to RW, and this H is equal to HW. This is one condition. This is as like as one observation well, because main well act as an observation well. And another extreme condition is R is equal to capital R, that is capital R means that is the radius of influence, that is from the center of the well to the extreme conditions. This is touches here, this is the where the line touches the water table, that point to the center of the well is known as radius of influence. This is the radius, this is capital R. Here R equal to capital R. Once we are going to take R equal to capital R, H is equal to total depth of water H. These are the conditions. Now we are going to use, then we have the another formula. So as like as earlier one, H heads are arranged one side and R related heads are arranged in the another side. Now we are going to take the limits as like as R equal to RW, H is equal to HW, R equal to capital R, and H is equal to capital H. So based on that limitations, finally we have one equation here, pi k h2 square minus hw square by log e r2 by r by rw. This is also as like as earlier formula. Earlier what we have, pi k h2 square minus h1 square divided by log e r2 by r1. But here pi k is constant as like as earlier one. Here earlier we have taken observation well number 2, that water depth is h1. Here we have taken extreme conditions outer, that is h. Here inner well earlier h1, here main well hw. Here R is the extreme condition R, earlier case is the R2 by R1, here R by RW. Same formula. That is earlier case we have taken observation well number 1 and observation well number 2 with respect to point P. Now we have taken with respect to point P main well and extreme conditions. So this is the formula used for the determination of flow rate into well through an unconfined aquifer. Then confined aquifer. So here also the determination of flow rate to the confined aquifer also as like as unconfined aquifer. Here the difference is in case of unconfined aquifer, the depth of water is nothing but bottom of the layer, that is impervious layer to the water table, that is H. Whereas in case of confined aquifer itself, it is the confined between the two impervious layers. One is impervious layer bottom side and another impervious layer on the top. The water is confined or bounded and are closed in between two impervious layers. That thickness is known as B. Earlier we have taken the water level to the impervious layer. Here we have taken two impervious layer thickness, that is denoted by B. This is the difference between the unconfined aquifer and confined aquifer. Remaining all heads are same. Here we are going to install one piezometer. Digging well in confined aquifer, the water level will be raised up to the pressure head. That means piezometric level. Now this is the diagram. Well is penetrated or digged in confined aquifer. This is the ground surface. This is the impervious layer. This is the another impervious layer. Here this is the, because this is confined aquifer located in between two impervious layers. So here dig one well, the water level will be raised like this up to this one. This is known as a piezometric surface. In case of confined aquifer, this line is known as piezometric surface, whereas in case of unconfined aquifer, this line is known as water table. Here also water is pumping through the well. Because of the pumping, here the earlier the water surface, that is the piezometric surface, is here. After pumping is started, the water level will be fall down from this level to this level. This is the drawdown. This is also denoted by SW as like as unconfined aquifer, and the water depth in the well is equal to HW. This is also as like as unconfined aquifer. And also here this is as like as earlier case, this is the cone of depression. Cone of depression, this is the drawdown curve. Yes, here also provided one point P. This is R from the main well, and water depth in the point P is H. And also I have taken two observation wells, observation number well 1 and observation well number 2. Here also as drawdown because of the pumping here. There is no pumping in the observation well number 1 and observation well number 2, even though the drawdown is possible here because of the pumping from the main well. So due to this pumping, the drawdown in the observation well number 1 is equal to S1. This is also as earlier, and observation well number 2 also drawdown S2. This is also same as earlier case. The water level in the well number 1 is equal to water level well number 2 is equal to H. So the extreme, that means piezometric surface to the bottom surface is equal to H. This is as almost all earlier case. Earlier the thickness is H because the water table to the bottom surface. Here thickness is B, that is in between two impervious layers. Here also we are going to take based on the Darcy's law, V is equal to Ka, I is equal to dH by dr, and also discharge for estimation of discharge, Q is equal to velocity into cross-sectional area. Velocity is nothing but K into I. A is here the area the water joins into the well from the basis, from the surrounding, from the surface of the well is 2 pi RH in the earlier case. Here 2 pi RB is the area. Now Q is equal to 2 pi RB. Instead of H here we have taken B into K into dH by dr as earlier one. And also here we have taken all H related items are one side, R related, that means radial distance heads are comes into another side. Then here also we are going to take integration on both sides, and also taking the limits R equal to, as usual earlier case, R equal to R1, that means from this point to this point. At that condition H is equal to H1 and R equal to R2, that is the main well to the point P to the, this is equal to R2, right? Here as whatever we have used the limits in the unconfined aquifer, same limits are used here also. Then finally here, because of the earlier case, here we have HDH, because of the integration have a square parameter here. Finally, the formula is 2 pi bk H2 minus H1 divided by log E R2 by R1. This is the final formula for the determination of flow rate into a well through confined aquifer. Water level in the observation well number 1 and also water level in the observation well number 2, then only we are going to use this formula directly. If they have not given H2 and H1, because these are the water levels available in the observation well number 2 and observation well number 1, if they have not given water levels, instead of that they have given drawdowns. That means instead of H1 and H2, they are going to give S1 and S2. What we are going to do now? Right here, apply one technique that is H is equal to total from piezometric surface to the this level, total is equal to H. H is equal to what? In case we are going to consider observation well number 1, H is equal to H1, that is from this point to the bottom, H1 plus S1, then S1 is equal to capital H minus H1. Like that, in case of observation well number 2, H is equal to H2, this point to this point, H2 plus S2, then S2 is equal to H minus H1. So by substituting these two values in this equation, if necessary, here finally you have instead of this one H2 minus H1, instead of that S1 minus S2. Here in this case H2 is nothing but capital H minus S2 minus here capital H minus S1. Finally you have instead of H2 R1 instead of H1 R2. Then we are going to discuss about these R1, R2 related formulas.